It's a universal law of great utility. The next question is, of course, what's x? After all, it's an interesting law to discover because it's the same for all machines and doesn't depend on any particular one, so I can get the x that way. One way is to invent a reversible machine and figure out how high it lifts. But I have a more ingenious argument for you that tells us what x is, and so I'd entertain you by the following argument. Suppose that we have a reversible machine which is going to lift this distance x, 3 for 1. I set up a set of 3 balls here. This is only a rack to hold the balls and it doesn't move. This ball is being held on a stay up here at a distance 1 foot above the ground. The machine lifts, if I put, this is the other part, this is the machine here. This platform and this piece here. And the machine is of this nature that if this goes down 1 foot, it can lift 3 balls, lowering 1, by a distance x. Now I arrange that the platform which holds the 3 balls has 3 shelves, or 2 shelves on the floor, 3 shelves, exactly spaced at distance x. And I further arrange that my rack which holds the balls over here are all spaced at distance x. I measured the distance x and I found out what it is, and so I laid this thing out and I'm all ready for the argument. Now first I roll the balls from here to here, and I suppose that takes no energy because I don't change the height. So I load the balls onto the platforms, and I get into this condition. Now, the machine operates in the way it's supposed to operate. This reversible machine operates. It lowers this ball to the floor, and it lifts this rack a distance x. Now you see how cleverly and ingeniously arranged is this rack here. These are spaced at a distance x, and so these balls are right even with the platforms that they can be rolled out onto, and so I unload the balls here. Now, having unloaded the balls, I can restore the machine to the original condition without the ball. That's the property of the machine, that it can be, that after you lift the weights, you can restore the machine to this original condition without any extra energy. So now I have 3 balls on the upper 3 shelves and 1 down here, naturally, having lifted essentially these 3 balls up. But you see, the funny thing about it is that in a certain way of speaking, I haven't lifted these 2 at all, in a way of speaking. Because after all, there were balls on that shelf before. There are still balls on those shelves. So in net resulting effect of the whole thing really has been to lift the ball from here to here. 1 ball, see? Net result. In order to illustrate better, suppose that we rearrange the balls by moving this one over here and this one over here. Then you'll see better what I mean. Now I roll this ball into this hole and roll this ball across over to this position. Then you'll see that these 3 balls are just exactly the same as they were in the initial condition, but that the 4th ball here is at some other height, which is 3x. If this 3x exceeds 1 foot, then I can lower the ball from here to here running some other machine and getting power free, and then I'm back in the initial condition and can run my apparatus again. Therefore, 3x cannot exceed 1 foot. For 3x exceeds 1 foot, I can make perpetual motion. Now, likewise, you can prove that 1 foot cannot exceed 3x. I leave it to you to work it out. All you have to do is to start around the other way, make the whole machine run the opposite way. It's a reversible machine, and the same argument can be carried the other way in which you lower things. In other words, if the 3x were lower when you started out than the 1 foot, then you can show by running the same argument in the opposite direction that you would make perpetual motion. Therefore, 3x is neither greater nor less than a foot, and we discover then by argument alone the law that the x is 1/3 of a foot. I'm sure the generality is clear to you that if 1 pound falls a distance, a reversible machine can lift 3 pounds to 1/3 the distance. Or if 1 pound falls a certain distance in operating a reversible machine, then the machine can lift p pounds a pth of the distance, 7 pounds a 7th of the distance, and so forth. And that now gives us the law of, we can state the law of the conservation of energy this way. Then another way to put the same thing is the following, that 3 pounds times the height lifted, which in our problem here was x, is equal to 1 pound times the height, the distance lowered, which is 1 foot in this case, or 12 inches or whatever you want. Excuse me. Yeah. So, another way of saying this is the following. If I take all the weights and multiply them by the heights that they are now above the floor, all weights in the problem, multiply all the weights by the heights above the floor, and then let the machine operate, and then multiply all the weights by all the heights again, there'll be no change. That is the sum of this for all the weights. This symbol means add. Weights times heights for all the different weights added together is unchanged. We'd have to generalize this single case where we moved only one weight to the case where when we lower one, we lift several different ones. But you can use the same kind of arguing to deduce this too in a more general case by having more elaborate machines. I just illustrate the type of reasoning, but this is deducible from this type of reasoning. That is, if we take the machine, for instance, that starts with one up here at a foot high and 3 on the floor, and then after the machine is operated, the 1 is on the floor and the 3 is up in the air by the distance x, then the way of calculating this way is the following. In the beginning, it's 1 pound by 1 foot. That's for the first weight, plus 3 pounds times 0 feet. How convenient, it's easy to calculate it. And that turns out to be the same as 1 pound times 0 feet plus 3 pounds times x feet. Of course, it checks every time. That's why I'm telling you about it. It's the same thing. This, we call this term, the sum of the weights times the heights, gravitational energy. The energy which an object has because of its relationship in space relative to the Earth. And the formula for gravitational energy, as long as you're not too far from the Earth, the force weakens as you go higher. So this is only approximate. You might try to find out where the error is in this analysis if the heights are so high that the force weakens. Gravitational energy has the formula, the sum for all the various particles. We don't have to remember the sum. It's always the sum of all the things that are there. You add it together. Weight times height. And that's an illustration of it. Now the question is, of course, it's a very beautiful set of reasoning. The only thing is, maybe it's not true. After all, nature doesn't have to go along with the reasoning. Perhaps, for instance, perpetual motion is in fact possible. So that some of the assumptions may be wrong, or I may have made a mistake in reasoning. So it's always necessary to check. And it turns out experimentally, in fact, to be true. Incidentally, the general name of energy, which has to do with location relative to something else, is called potential energy. In this particular case, more specifically, I would call this gravitational potential energy, to give you a high-class word. If it's a question of electrical forces against which you're working, instead of gravitational forces, you're lifting charges away from some other charge with a lot of levers, then the energy content is called electrical potential energy. The general principle is that the change in the energy is the force times the distance that it's moved, that your force is pushed. And that's a change in energy in general. But we come back to a lot of these things and make them when we go on with the course, of course. Now this principle, the conservation of energy, is very useful for figuring out what will happen in a number of circumstances. And I'll illustrate some of those. Just because you probably learned an awful lot of laws in high school to figure out what